Good morning, students. Let us discuss Green's theorem in a plane today. So Green's theorem, which relates the line integral and the surface integral. So we can transform double integral into single integral. We can transform the surface integral into line integral. So most probably in Green's theorem, we will be discussing only the surface integral. So we will get some answer that will be equivalent to line integral. It's easy to calculate the area enclosed by a curve C. So we will be solving only surface integral. That will give us the answer for the line integral. So it is the special form of Stokes theorem. Let S be a closed surface in a plane enclosed by a curve C. So we have a surface S. This is enclosed by a curve C. Okay. If M and N are continuous and differentiable scalar functions of x and y in S. So we have a surface which is enclosed by a curve C. Okay. So we have an area which is enclosed by a curve C. Now you are going to draw two parallel lines. See, two parallel lines parallel to y-axis. So we are going to draw two lines which is parallel to y-axis. These parallel lines, they cut the point in the curve A and B. Correct? So we have two parallel lines parallel to y-axis and they intersect the point A and B. Similarly, we are going to draw two parallel lines parallel to x-axis and they cut the point E and D. So this is the idea. Now we have two curves. One goes from A to B. Another curve goes from B to A. So A, E, B, which is denoted as C1. So which is equal to f of x, which is a function of x. Similarly, B, D, A, which is nothing but C2 curve, which is nothing but g of x. Your total curve C equals C1 plus C2. So this is a description of the figure. And the Green's theorem, mainly the statement is like this. So we have a single integral m dx plus n dy, where m and n are continuous and differentiable scalar functions, which is equal to double integral dn by dx minus partial dm by dy dx dy. So this is a statement. So as we discuss the descriptions which are given on the slide. So we have descriptions now. You have f of x. The main condition is less than or equal to g of x. Now you are going just to consider the second term of the right hand side of equation 1. So we have equation 1. We are going to consider this term. So this is equation 1. We are going to consider the second term. We are going to consider the second term. Second term is nothing but double integral dm by dy dx dy. So we can write there are two integrals. So limit goes from one limit goes from A to B. Another one is f to g. See, just one goes from, this is your A, see A, this is B. So it goes from A to B. Another one goes from this side. So y equals f to g. Okay, f to g. dm dy dx. And after the integration, we will get the answer as m, which is a function of x comma y. Correct? So in the integral, we have integrand. We are going to take the integral. So after integration, we have answer as m, which is function of x comma y with the limit f to g. Upper limit g, lower limit is f. You have to substitute only for y. Okay, not for x. So now this becomes m of x comma, instead of y you have to substitute the upper limit. So g minus, instead of y you have to substitute the lower limit. So we have f. Is it okay? Now look at the figure. So it goes from A to B. Then here it is B to A again. It is reversed. Correct? Look at the curve. It goes from A to B, again B to A. But look at the integrals. This is A to B. This is also A to B. But this is G. See, m, which depends on G. G goes from B to A. It is not from A to B. So we'll have to reverse the integral. Is it okay? We'll have to reverse the integral because it goes from b to a, not a to b. So we'll have to reverse it. So when you're going to reverse it, you're going to change the limits. When you're going to change the limit, becomes minus b to a. Now it's correct. So m as a function of x comma g, and here m as a function of x comma f. Okay. So this is your C2 curve, and this must be your C1 curve. So generally we can write g of x. Look at the figure now. G of x is nothing but C2. Your f of x is nothing but C1. So this is for C1 and this is for C2. See, this is for C1 and this is for C2. And we know that C1 plus C2 equals C. So we can write this. So we have found out the second term of the right hand side answer as this one. We have found out. Similarly, one can also get the first term. The first term of the right hand side, that goes like this. You have n dy. Here it is m dy. See, after the integration you will have m dx. So we have m dx, and here it is n dy. We are going to add these two. So when you are going to add these two, you will get like this. Okay. So I have interchanged this one. So this is line integral into surface integral, which is nothing but Green's theorem. So this is Green's theorem. It establishes a relationship between the line integral and around a simple closed curve and a double integral over the region enclosed by that curve. So this is the proof of Green's theorem, which is very, very important as far as this vector calculus is concerned. Now let us solve using Green's theorem some problems. Using Green's theorem, we are going to evaluate this. So this is a line integral, see, single line integral, where C is a boundary describing y equal to x in a counterclockwise with a triangle with the limits will be 0, 0, 1, 0, 1, 1. So y equal to x, so it must be a straight line equation. So y equal to x, y equal to x, C equals 0, y equal to mx plus c. Can you remember the equation of a straight line? Here m equals 1 and c equal to 0, so y equal to x. So you have the curve like this. So it's a straight line equation where c equals 0. Okay, y equal to mx plus c, m equals 1, so y equal to x. What are the limits? So it starts from 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, and it's given us counterclockwise. So counterclockwise is this one. So this is your clockwise, this is counterclockwise. Correct? So this is your clock. So this is your counterclockwise, anti-clockwise. You see, now you are going to evaluate the single integral. As I said earlier, that it's easier to solve double integral, as I said earlier, and we can get the answer for the single integral. Is it okay? So as per the Green's theorem, so we have this Green's theorem is given by this, and we know that m dx plus n dy, m dx plus n dy is nothing but x squared y dx plus x squared dy. You compare this equation, and we have m dx plus n dy is given by this. So compare these two, the coefficients. We have m dx equal to x squared y dx, correct? And your n dy is nothing but x squared dy. Just to compare the coefficients dx and dy, we will get this. Okay, we need to have dn by dx and dm by dy. So m is given as dx, ds will cancel, m is given as x squared y. Differentiating with respect to y will give you x squared. So here also n dy equal to x squared dy, so n equals x squared, differentiating with respect to x. Okay, we will get 2x. So now you can substitute for dn by dx and dm by dy. So we have substituted now. We have substituted the values of dn by dx and dm by dy. So we can, in the double integral, we will have this expression, correct? So we have now, see, 2x minus x squared. See, 2x minus x squared dx dy. What are the limits? So we have limits. The condition is given as y equals x. Y equals x. So the limit that for y goes from 0 to x. 0 to x. And for x it is 0 to 1. So this is 0 to 1 and this is for 0 to x. So now 2x minus x squared dx dy. After integrating, you will have y, the limit is 0 to x. So we have 2x minus x square dx x. You multiply with x, that will give you 2x cube by 3 minus 2x square minus x cube. After the integration, you will have 2x cube by 3 minus x to the power 4 by 4 with the limit 0 to 1. You substitute for x now. So we will have 2 by 3, 1 cube minus 1 by 4, 1 to the power 4. And lower limit will be 0. And we have 2 by 3 minus 1 by 4, taking the LCM, that will give you 5 by 12. Okay, 8 minus 3 divided by 12. So 5 by 12, we have obtained the right hand side, which is equal to the answer for the left hand side, which is asked. See, this one is asked. We have found out the answer for this. So which is equivalent to this. Okay, simple problem. So we have evaluated the line integral which is asked in the problem, which is equal to 5 by 12. Any doubt? Okay, very simple problem. Now verify Green's theorem. So now we have to verify. Earlier, in the earlier problem, we evaluated the left hand side, correct? We evaluated the right hand side, which is equal to the left hand side. Now it is asked to verify Green's theorem. So you have to evaluate both the sides, left hand side as well as right hand side. Both the answers should be the same. Is it okay? See, we are going to evaluate, as per the Green's theorem, we are going to evaluate both the sides, double integral. We will get some expression, we will get some value. Similarly, we will evaluate for the right hand side. Again, we will have one value. These should be matched. Okay, this should be the same. So verify Green's theorem in the xy plane for this problem, where C is the boundary of the region given by x equals 0, y equals 0, and the equation is given as x plus y equals 1. X plus y equals 1 goes like this. This is where x plus y equals 1. So this is the line. So equation of x plus y equals 1, the graph goes like this. And x equal to 0, y equal to 0 is given. See, origin is 0, 0. So when x plus y equal to 1, when x equal to 0, you have y equal to 1. When x equal to 1, you have y equal to 0. Correct? You substitute here. When x equal to 0, you have y equal to 1. Correct? When y equal to 1, we have x equal to 0. So according to this, we will have 1, 0, and this must be 0, 1. Is it okay? This is 0, this is 1, 0, and this must be 0, 1. And we have the figure x plus y equal to 1. The equation of line has been drawn here. Now, according to Green's theorem is given by this statement. So this is your Green's theorem. And this is the problem. In the problem it is given. You compare this one and this one. When you are going to compare this one and this one, we have m dx plus n dy is nothing but this. So we have m equals 3x minus 8y squared, and your n will be 4y minus 6xy. Is it okay? And just to differentiate m with respect to y, that will give you minus 16y, correct? So this becomes 0, this becomes minus 16y, and your dn by dx will give you, this becomes 0, correct? With respect to x only we have, so this becomes 0 and this becomes minus 6y, okay, minus 6y. Is it okay? Now we have found out now dm, dy, dn, dx, and the problem is given as this is one line, connecting line, this is another line, and this is another line. So curve is closed curve is starts from 0 to A, then A to B, then B to O. So we have three curves now. One is this one, another one is this one, another one is this one. So we have three curves now. So we have now left hand side. Left hand side is a closed curve. So closed curve, total closed curve, which is equal to O to A to B, then B to O. So we are going to calculate, we are going to evaluate each integral, and we are going to add. So that will give us the answer for the left hand side. So first we will evaluate this. Is it okay? Evaluating that will give you O to A. So for O to A, y equals 0. Okay, x alone exists, y equal to 0. Whereas for O to B, x equal to 0, y alone exists. So now O to A. So first we will evaluate, we are going to evaluate this integral. So O to A, and of course your n are given by this, and it's given as y equal to 0, correct? As per the problem, your y equal to 0. So when y equal to 0, dy equal to 0. So dy equal to 0, this term will go off. Dy, this term will become 0. 0. Correct? When y equal to 0, this term will become 0. So we have only 3x alone. 3x dx. So integration will have 3x squared by 2. Substituting the upper limit will give you 3 by 3 by 2. 1 by 2 multiplied by 3 will give you 3 by 2. So we have evaluated one integral. So next integral will be AB. AB, the line, the equation is x plus y equals 1. See here, AB. x plus y equals 1. So y equals 1 minus x. So dy equal to minus dx. So instead of dy, you have to substitute minus dx. Similarly, instead of y, you have to substitute 1 minus x. So 3x minus 8. Instead of y, you are going to substitute 1 minus x whole square. 4. Instead of y, you have to substitute 1 minus x. And instead of y, you have to substitute 1 minus x. So 3x multiply, and this can be expanded to a minus b whole square formula. So 8, 1 minus 2x plus x square dx, and this must be your minus sign. I have brought it front. So minus dx. See here, minus dx. So minus is here. So you have 4 1 minus x minus 6x 1 minus x. So multiplying with the 8 will give you this. We have 3x minus 8 minus plus. So 16x minus multiplied by plus will give you minus. So minus 8x squared minus 4, and this becomes plus 4x, and this becomes minus plus 6x, and this becomes minus 6x squared. Minus multiplied by minus, another minus is there. So we have minus 6x squared. So minus 8 minus 4 will give you minus 12. 3x plus 16x plus 4x plus 6x will give you 29x. Remaining minus 8x squared minus 6x squared will give you this. I have written the same thing here, and integrating, that will give you, on integration, that will give you minus 12x plus 29x squared by 2 minus 14x cubed by 3. But look at the limit, it is 1 to 0. It is not 0 to 1, because we are going in a reverse way. See here, we are going in a reverse way. So it is 1 to 0. Okay, it's very important. It is not 0 to 1. So this is 1 to 0, reverse way. So the limits, look at the limits. Limits will be 1 to 0. So substituting the upper limit will give you 0. Substituting the lower limit will give you minus 12 plus 29 by 2 minus 14 by 3. Take the LCM. So that will give you 6 here. So we have 6 12s are 72 minus, we have 3 29s are 87, 2 14s are 28. You add all those things, that will give you 13 by 6. So we have calculated second integral. Now we have to calculate one more integral, B2O. B2O will give you x equal to 0. Can you remember? B2O will give you x equal to 0. So now B2O. So we have m and n, x equal to 0 and dx equal to 0. X equal to 0 implies that this term will become 0. Here x equal to 0, that will give you, this term will go off. We have only 4y alone. So we have 4y dy. So upon integration, that will give you 4y squared by 2. Substituting the upper limit and lower limit will give you 4 multiplied by minus 1 by 2. So that will give you minus 2. So now we will have to add all the line integrals. O to A to B, B to O. So 3 by 2 plus 13 by 6 minus 12. Take the LCM. So that will give you 10 by 6, which is nothing but 5 by 3. So which is the left hand answer for the left hand side, which is the line integral. Now we have to calculate the right hand side, which is the area. So this answer, you just remember, this is 5 by 3. We have to get the same answer. Okay, let us see. So right hand side of Green's theorem is given by this. So double integral, we have partial dn by dx minus partial dm by dy multiplied by dx dy. And of course we know already dm by dy already we have calculated. Dn by dx also we have calculated. You substitute for dn by dx, dm by dy, dx dy with double integral. Simple one. So minus 6y plus 16y will give you plus 10y. So plus 10y, correct? 16 minus 6, so that will give you 10y. So 10y dx dy. So what are the limits? So limit, one is from 0 to 1, another one is from, see, x plus y equal to 1, it's given in the problem. So we have x equal to y minus 1, correct? X equal to y minus 1. So your limit for x will be 0 to 1 minus x. So 0 to 1 minus y. That's a mistake here. This is x plus y equal to 1. So your x will be 1 minus y. It is not y minus 1. So that's a mistake here. Okay. It is x plus y equal to 1. So x equals 1 minus y. So x goes from 0 to 1 minus y. X has a limit 0 to 1 minus y. Y has a limit 0 to 1. So y dx dy. So now y, instead of dx you'll have to integrate, that will give you x 0 to 1 minus y. Substitute the upper limit, that will give you 1 minus y, and you have y into 1 minus y will give you y minus y square dy. So I have written the same thing here. So 10 times I have integrated now. So y squared by 2, it becomes minus y cube by 3, 0 to 1. Substitute the upper limit will give you 1 by 2. Substitute the lower limit will give you 1 by 3. Take the LCM. So that will give you 10 by 6, which is nothing but 5 by 3. So which is exactly equal to the left hand side. See? So we have verified now Green's theorem. We have verified Green's theorem. Is it okay? Simple problem.